Oh, sorry. I constantly muted on this thing, huh? Okay. It was just a reiteration from last time. Sorry about that. So what we're doing is looking at this curvature, right, from last time. It's the magnitude of our unit tangent vector. And how it changes with respect to arc length, right? And this arc length is an inherent part of the curve, right? So this curvature is an inherent way to kind of measure how curvy the curve is, right? We're not, no matter what parameterization we use to define our curve, this will always be the same exact value at that point because we're using inherent properties of the curve itself. It's a unit tangent at that time and its arc length. So we noted that the unit tangent is typically, we write it in terms of it's some dummy parameter t. And if we took a derivative with that, we had our unit tangent. And we could write it as ds, and then how the arc length changes ds with respect to time. Okay. So that means that we can write how the unit tangent changes with respect to arc length as the fraction of how the unit tangent changes with respect to t, and how the arc length changes with respect to t. So at the end of yesterday's lecture, we said that kappa could also be written as, let's actually write it like a little bit neater because we have a fraction here. How the unit tangent changes with respect to t over the magnitude of how the arc length changes with respect to t. And that's where we left off from last time. So I want to look at this denominator for a second here, right? This is the absolute value of this property ds dt, okay? Well, what is ds dt? Can we rewrite this in some way? So s is this arc length, and this is asking how the arc length changes with respect to time. So we can take a kind of verbal approach while we're kind of just talking through it, or we can kind of brute force this and figure it out. So let's take the verbal approach first while we're thinking, well, arc length kind of represents the distance traveled, right? If I start at some spot and I end at some other spot, my particle has traveled along this line here. Then how that changes might be kind of related to velocity, but remember this is a scalar, so we can kind of think that this might have something to do with speed. Okay, so we have our guess. Can we show that this in fact is the speed? So note that I can write down the arc length at a given time that starts at some location, and we'll call that t naught, and it goes out to t. Remember, arc length was the speed of the particle, and we can't use t again here, so we'll use just some dummy variable. We use u here, du, right? So we're going from some fixed point in time, and we're going out to some arbitrary point in time, and this is the function of arc length, right? So it takes time in, and it gives us how far we've traveled since time t naught, right? So if I have this as my s, this is my arc length function, and I'm taking this time derivative of it, you can think of the fundamental theorem of calculus, right? This is, we're going to cancel out this integral, and our t will go inside of our integrand. So using the fundamental theorem of calculus, we say that ds dt is the integrand with our bound inside. And then we get the magnitude of r prime of t. But remember, r prime is the velocity, and the magnitude is simply just the speed, right? So it looks like this fraction that we have in the denominator is the speed, right? And even just taking the magnitude of this guy is fine because this is always going to be a positive quantity anyway. So with that, we can write that the curvature as a function of time is then the derivative of the unit tangent over the speed at time t. Okay, so that's yet another way for us to write down this curvature as a function of t, but I'm not satisfied yet. This t prime can kind of be massaged into some other stuff, right? So what is t prime? So t is this unit tangent vector, the vector that's pointed in the direction that velocity is, but now we're taking its derivative. So it's not quite acceleration, right? Because it's this normalized direction for velocity, and I'm taking how that thing changes with respect to time. Okay, so let's kind of work through this numerator here and see if we can rewrite this. So let's keep going. What we're going to note moving forward that we have that the unit tangent's definition was r prime over the magnitude of r prime. And we also noted that the magnitude of r prime is ds dt, right? So that was our definition, and we just showed speed is equal to the change in arc length over time. So what I'm going to do is I'm going to look at r prime. From this relationship here, I can note that r prime is the speed times the unit tangent vector. And that makes sense, right? I have my direction, this t, and then I have my magnitude, the speed, and that gives me my velocity. Okay, well, let's take it a step further. This here is equal to ds dt times our unit tangent, right? So now all I've done is subbed in the speed for our ds dt for the speed here, right? So this is how the arc length changes with respect to time. What happens if I differentiate this line now? So if I wanted to find r double prime, I have to look at this right-hand side here, and I have to do a product rule. So I'll end up with the second derivative of arc length with respect to time times our unit tangent plus how the arc length changes with respect to time times t prime. Okay, so here's our t prime. So this might be some way to kind of figure out some way to solve for this t prime and place it into our definition up here in this numerator for curvature. So you probably can't guess what the next step is here. We're not just going to just solve for it immediately because we don't really know what this term is here. So we are going to note the relationship for the cross product of r prime and r double prime. So we're just kind of taking a shot in the dark. You got to trust me on this. We're going to look at what happens with this cross product here. Maybe I can get something kind of useful, and you can see why we do this in a second. So if I do r prime and I cross it with r double prime, because these are two terms here, what I can do is kind of split it up. So I know that r prime, so let's kind of, r prime is this ds dt times our unit tangent, and our r double prime is this two-term right-hand side right here. So what I'm going to do is split up this cross product into, they both share the same left-hand side. So ds dt t crossed with the second derivative of arc length as well as the second term, which is ds dt t crossed with ds dt t prime. So all I've done is just distribute this cross product here, right? Because we have our ds dt and it's crossed with both of these terms here. So we have ds dt on this first term and then ds dt crossed with the second term here. Okay, so now let's look at these individually. We look at this first grouping and we notice that we have got a scalar function out in front of this t, and as well as another scalar function in front of this vector function t as well. So it looks like these vector functions scale the magnitude of each term, but the direction itself will always remain the same. They're always pointed in the t direction. And now I'm taking their cross product. Well, the cross product of two things that are parallel, right, should give us 0, right? There is no really nice vector that's, or every vector is orthogonal to the same vector, right? These are parallel things. So this result ends up just being 0 here, right? These are parallel vectors. So this is equal to 0. So we just have this last term here that remains. And notice that they both share a ds dt. So what I'll do is I'll pull those out. And because they're in each cross product, right? So if there was a scalar function out in front of one of them, we were able to pull that out. But if it's out in front of two of them, we need to pull both of them out, which results in a ds dt squared times the quantity t crossed with t prime. Okay, so now we've got this t cross t prime, and we have to kind of finagle this guy and see what we can come up with. So to kind of get an idea of the relationship between this term here and our term that we finally arrived at over here, let's look at the magnitude, because these are cross products, right? So the cross product, the magnitude of the cross product will be ds dt squared, so this is always a positive quantity, times the magnitude of this cross product, the unit tangent crossed with the derivative of the unit tangent? Well, using the properties of the cross product, specifically the magnitude of the cross product, we can break this into the magnitude of t, the magnitude of t prime times sine of theta. Okay, so I know what the magnitude of t is, right? It's a unit tangent vector. So I know that this term here is just equal to 1, right? We also know what this angle is, because if we recall from earlier, since the unit tangent vector is a constant length, that the magnitude is equal to 1, we know that it's orthogonal to its derivative. So we talked about that yesterday, right? We had these vector that had constant length, and we realized that in that special case, that these vectors always were orthogonal to its derivative. So if it's always orthogonal, we know that sine of theta is equal to 1. Which means that the magnitude of r prime crossed with r double prime is equal to ds dt squared times the magnitude of t prime. Okay, so that was a long journey. Where did it get us? So note that above, that's exactly what that we were looking for. We were looking for the magnitude of t prime, right? And there it is, sitting right here. So thus, the magnitude of t prime is equal to the magnitude of r prime crossed with r double prime all over ds dt squared. But remember again that this ds dt, this is just the speed. So we can just write this as the magnitude of r prime crossed with r double prime all over r prime in magnitude squared. So we finally arrive at another definition for our curvature, since we were using the magnitude of t prime over the magnitude of r prime, we can substitute in our expression for the magnitude of t prime. This is r prime crossed with r double prime all over the magnitude of r prime cubed. And this is most likely the approach that you'll use most of the time, right? Because we'll give you some parameterization, or maybe you find the parameterization yourself, and you have r. Well, then it's easy to find r prime. It's easy to find r double prime. And then we need to look at the magnitude of their cross product as well as their magnitude of r prime. And then there, we have curvature as a function of t. So we were able to plug in some t value and know exactly what the curvature is at that specific location. Okay, so that was a little bit lengthy, but we found it. We found this really nice form for our curvature. Now you could just do this guy here. It might be a little bit more work sometimes, but there are definitely spots where perhaps this is easier, where maybe you already have the unit tangent, so you simply just have to take the derivative. But if you're starting from scratch, I would recommend this guy over here. Okay, let's do an example. So we're going to find the curvature of the helix A cosine t, A sine t, B t. Okay, so we have some helix. Looks like it's slowly moving up in the z direction, and we have a circle of radius a. So the first thing to do is find this r prime. So we'll go ahead and take its derivative. So we'll get negative a sine of t, a cosine t, and b. We're going to need r double prime, so we might as well calculate that now as well. So we have r double prime of t is equal to our negative a cosine of t, negative a sine of t, and 0. So we're going to need the cross product of these two guys. So r prime cross with r double prime is equal to, we're writing it as our little determinant here. So we'll have our I hat, and then negative a sine of t, negative a cosine of t, our j hat, our a cosine t, negative a sine of t, and our k hat is b and 0. Okay, so we go ahead and do this cross product. So the x element will be the determinant of this 2 by 2 here. So it looks like we get a 0 times an a cosine t, which is nice. And then we subtract this b times this negative a of sine of t. So all that's left is an a b sine of t. The the y component will be the negative of the determinant of the block that's created from this column and this column. So I'll have this 0 times this negative a of sine of t. That's also nice. And then we have b times negative a cosine of t. So here we'll get negative AB cosine t. And then for our z component, we're looking at the determinant of this block here. So we have a squared sine squared of t plus an a squared cosine squared of t. But that's really nice because we have a sine squared plus this cosine squared. So we can simplify this just a little bit. So we get the vector AB sine of t negative AB cosine of t a squared. Okay, so now that was the vector of our r prime crossed with r double prime. We still need this vector in magnitude. So we have r prime crossed with r double prime is equal to the square root of a squared b squared sine squared of t plus our a squared b squared cosine squared of t plus a to the fourth. Should the x component be negative? I believe it should not be negative because we have negative b, so we're subtracting this here. So this should be negative ab sine of t, but we're subtracting this, so it should be positive. So luckily, again, we have this sine squared, cosine squared. So this is a squared b squared plus a to the fourth. Or we can write this as a times the square root of a squared plus b squared. So that was the magnitude of our cross product here. So let's also look at the magnitude of r prime. This is the square root of a squared sine squared of t plus a squared cosine squared of t plus our b squared. And once again, we have this sine squared cosine squared. So here we just have a squared plus b squared in a radical. So our curvature is kappa of t, which was our magnitude of the cross product between r prime and r double prime over the magnitude of r prime cubed. So this is a square root of a squared plus b squared over the square root of a squared plus b squared cubed. This just leaves us with a over a squared plus b squared. That's pretty nice form considering all of the work that we went through, right? So it's a little bit longer than some of the other problems that we've done so far, but kind of expect that. We're kind of getting into the calculus now of all of this. So the basic premise was we found our prime, our double prime. We took the cross product to form the numerator. We had to take the magnitude, and then we just took the magnitude of r prime, and then just plug and chug into our formula here for the curvature. And there we have it. There's the curvature for our specific helix. Let's define one last thing. I think it'll take us a few minutes, and then we'll take our 5-minute break, and the TAs will show up shortly after that. So let's do one more definition. So moving forward, we're going to talk about the normal and binormal vectors. So we can define the unit normal vector as we use a capital N for this. So capital N. This is T prime over the magnitude of T prime. So basically, this is the unit vector that kind of characterizes how the unit tangent vector is changing with respect to time, right? Because when you take this derivative of the unit tangent vector, you might not be left with another unit vector anymore. So we have to renormalize. So we take the derivative of the unit tangent, and then we renormalize from there, and that creates this normal vector. So since T prime is orthogonal to T, right? That's something we talked about above, right? When we have a constant length vector function, and we know that its derivative is always going to be orthogonal to it, we find one more vector orthogonal to both. So imagine that you're in some plane and you've got T, this unit tangent vector, and now we have this unit normal vector. They're both at 90 degrees with one another, but we're in R3, right? So we can fit in another vector that's orthogonal to both of those. And using all three of those things, we can kind of build a new Cartesian coordinate system. So what do we call this third vector? This is called the binormal vector. which we'll denote with a capital B. And it is the cross product between the unit tangent vector and the unit normal vector. So that creates 3 orthogonal vectors. And this T and B, so that we kind of call this for the unit tangent, the unit normal, and the binormal vectors. And we call this whole framework the T and B frame. This is very useful in differential geometry. So you might be asking, what's one example where this T and B frame might be useful? So imagine you are on a bus, you're just riding this bus, right? So actually, the whole way that you experience life is in the T and B frame, right? You don't see it as some outside observer that's got some stationary origin, right? You kind of experience life in this T and B frame because you yourself are this moving coordinate system. And that's what this T and B frame is like, right? So as an outside observer and you're standing still, you can kind of see these cars go by and you're like, oh, okay, I can set this as my, Cartesian focal point, or like this origin, and all these cars are moving. But if you're in the car, right, it looks like that person watching you from outside is moving, right? Because this is a different reference frame. This is what we can kind of consider this T and B frame, right? So this is useful when we're doing like classical physics or even higher end physics. But the T and B frame is pretty important for kind of moving our perspective. With that, why don't we take our 5-minute break, and then the TAs should be on shortly and they'll pick up with recitation. So I will see you all tomorrow. Stay safe. Take care.